Last time we were talking about bonding in general, and I left you the question of whether or not there was something in between, and maybe you thought, nah, there's nothing, but you knew there was. So today we're talking about polar covalent bond, and that is sort of the middle ground between purely ionic, and purely covalent. So we're still going to use the term covalent, but we're going to clarify or make it a bit more of a specific type of term. So we'll talk about covalent bonds, polar covalent bonds, and ionic bonds. Now, we already know about ionic bonds and covalent bonds, at least in broad strokes. And ionic bonds, we're not really going to do a whole lot more with that. Covalent bonds, as I mentioned, we are going to have to break it down or be more specific with what we mean by a covalent bond and what we mean by the other version of it, or the nuanced version of it. So if we go back to the periodic table, we're still mostly going to be dealing with the non-metal compounds. But if you think about what we know about trends in the periodic table, particularly with electronegativity, we've got a large range of electronegativities within that region of nonmetals. So when two nonmetals bond together, we still have different electronegativities. Now, if I start with what we are comfortable with, I suppose, with the covalent bonding between, say, two atoms of chlorine, where each chlorine has exactly the same amount of electronegativity, so exactly the same amount of pull on the electron, and so that the bond between those two things are going to be a perfectly shared pair of electrons. One chlorine has a certain amount of attractive force on that electron pair. The other chlorine has the exact same. So if you think about it as a tug of war, and it's not a very good way to think about it, but it works for what we're doing, both of those chlorines are equally matched. They are equally sharing those electrons. But if I look at something like hydrogen and chlorine, and in that situation, it's going to be a little bit different, because if I look at the periodic table and I find hydrogen and chlorine, yes, they're both nonmetals, so yes, they have quote-unquote slightly higher electronegativity, or their electronegativities are on the higher end of things, although honestly 2.1 for hydrogen is not particularly high, it's just higher than most metals. If I look at that, and they are going to be sharing electrons, and the reason they're going to be sharing electrons comes down to things like the lattice energy, which we're not really going to focus on too much, so we'll focus on the ionization energy. The ionization energy of both of those elements, particularly hydrogen, is high enough that the electron is not going to be pulled all the way off, but because of the difference in electronegativity, you end up with this electron being pulled toward the chlorine and a little bit less a little bit closer to the chlorine, a little bit further away from the hydrogen. And what you end up with is not an ionic charge, but something moving in that direction. So we call it a partial charge. And that little squiggle plus, it's actually the Greek letter delta and a lowercase delta. We have a partial positive charge on the hydrogen end of that molecule, or that bond, let's say, and a partial negative charge on the chlorine end of that bond because of those differences in electronegativity. Now, we generally don't write in the squiggle plus and squiggle minus, but we do need to understand that in a bond between two atoms, there can be a difference in electronegativity, which means there can be a partial charge. How large of a partial charge depends on the differences between the two atoms. Is it a significant difference? Well, again, it depends. And then what does it mean? Part of it, the answer is, it depends on how big the difference is, what we'll see in our physical properties, and not so much chemical properties, but generally physical properties. We will come back to that a little bit later on. If I were to look at, let's say, call it the electron cloud, so how the electrons are arranged around the atoms, the two, sort of the top left and the middle and the bottom, are the ones that we're familiar with, the purely covalent bond. This one is labeled as a non-polar covalent bond, which is probably a pretty good distinction to make, rather than trying to qualify that or assume that everybody knows what we talk about when we say a covalent, because covalent just means sharing. So non-polar, which means there's not a significant difference in electronegativity, so they're very equally sharing, compared to an ionic bond where they are not sharing them at all. And then that middle ground is a polar covalent, where they are sharing them, but they're not sharing them equally. So they don't have a full ionic charge, but they do have a partial charge. And I want to emphasize that there's this range of differences, and that's going to give us a range of partial charges. And so it's difficult for us to put hard and fast limits on this is going to be nonpolar, this is going to be polar, and this is going to be ionic, because of the nature of the bond is not a fluid thing, but there's a big range in between. So we do tend to talk about more nonpolar or more polar or less polar, more ionic, less ionic. So we can make those comparisons, say between these two, the difference is such that it's going to be a little bit more polar than this combination. Okay, it's going to come down to the electronegativity differences. Now for us, we're going to take ionic bonds as, or any metal-nonmetal compound as being ionic. And the reality is it's a little bit more complicated than that, but we're not going to get into the levels of complication, and we're not going to worry too much about it. So for us, metal-nonmetal is ionic. Any non-metal-nonmetal, now we have to dig a little bit deeper. If they are close in electronegativity, which means on the periodic table, are they close together on the periodic table, then they will be close in electronegativity, and that means they're going to be fairly nonpolar. Maybe not exactly nonpolar or purely nonpolar or completely, but they're going to be more nonpolar. And if they're further away on the periodic table, that means they're going to have a greater difference in electronegativity, which is going to make them more polar, or at least more likely to be polar, because if you were to start looking at the actual numbers, then you could probably find somewhere that the distance doesn't really help us as much. Now, please don't write these ones down. I mean, if you really want to, go ahead. The problem is two things. Number one, as it says right on the bottom, these numbers, these ranges are fairly arbitrary, but what I do want you to do is notice that a fairly small difference, from no difference at all up to about 0.3, we consider that to be nonpolar. So a slight polar charge is still going to behave mostly as nonpolar. And then the ionic range. I also want to point out the ionic range, that seems to be quite a large range to say, hey, all of those are ionic. And this is where I said it gets a little bit more complicated, but we're going to kind of ignore that. The other reason why I want you to not worry too much about these numbers is that you're generally not going to get the periodic table with the numbers. What you're going to do is not have that, but have this, where now I'm working with the trends in the periodic table, trends in electronegativity. So now I'm looking at, are they close together? Are they far away apart? Are they farther apart? Once they cross that staircase line that takes one of my elements into the metal zone, then I relabel it as ionic. Okay, not crazy difficult. Again, what it's going to come down to is being able to mostly rank them in order in terms of more polar or less polar, or at least maybe not rank them, because that suggests a longer list, but more comparing to. And then later on, that's going to lead us into something else where some of these broader physical properties, things like melting point, solubility, and so on. But that's a story for another day. See you then.